Factor analysis in a PCA from the original dimensions xi, I starting from 1 to 3 until d, we form a new set of variables z that are linear combinations of xi. Z equals to w transpose times x minus mu. In a factor analysis FA, we assume that there is a set of unobservable latent factors j starting from 1 to 3 until k, which when acting in combination generate x. Thus the direction is opposite that of PCA, see figure 6.4. The goal is to characterize the dependency among the observed variables by means of a small number of factors. Suppose there is a group of variables that have high correlation among themselves and low correlation with all the other variables. Then there may be a single underlying factor that gave rise to these variables. If the other variables can be similarly grouped into subsets, then a few factors can represent these groups of variables. Though factor analysis always partitions the variables into factor clusters, whether the factors mean anything or really exist is open to question. F8, like PCA, is a one-group procedure and is unsupervised. The aim is to model the data in a smaller dimensional space without loss of information. In FA, this is measured as the correlation between variables. As in PCA, we have a symbol x equals to the set x to the t, where the set is taken on all possible index t, drawn from some unknown probability density, with the expectations of x is equals to mu, and the covariance of x is equals to sigma. We assume that the factors are unit normals. Expectations of zj is equals to 0, and the variance of zj is equals to 1, and are uncorrelated. Covariance of zi and zj is equals to 0 when oi is not equals to j. To explain what is not explained by the vectors, there is an added source for each input, which we denote by epsilon I. It is assumed to be zero mean. The expectations of epsilon I is equals to 0 and have some unknown variance. The variance of epsilon I is equals to phi. These specific sources are uncorrelated among themselves. Covariance of epsilon I, epsilon j is equals to 0 for oi not equals to j, and are also uncorrelated with the factors. The covariance of epsilon I zj is equals to 0 for oi and j pairs. If A assumes that each input dimension xi starting from 1 to 3 until d can be written as a weighted sum of the k less than d factors, zj, j starting from 1 to 3 until k, plus the residual term, see figure 6.5, xi minus mu I is equals to vi1 times z1 plus vi2 times z2 and so on plus vik times zk plus epsilon I for all I starting from 1 to 3 until d. xi minus mu I in some sense will be equals to the summations of, if we summarize what we just described above, it will be the sigma vij zj, where the sigma is taken among index j starting from 1 to k, then plus epsilon I. This can be written in vector metric form as x minus mu equals to v times z plus epsilon, where v is the d by k matrix of weights called factor loadings. From now on, we are going to assume that mu is equals to 0 without a loss of generality. We can always add mu after projection. Given that variance of zj equals to 1 and variance of epsilon I is equals to phi, we know the following. Variance of xi equals to vi1 squared plus vi2 squared and so on plus vik squared plus v1. And the summations of vij squared summing with index j starting from 1 to k is the part of the variance explained by the common factors, and the phi is the variance specific to xi. In vector matrix form, we have sigma equals to covariance of x, which is equals to covariance of vz plus epsilon, which is equals to covariance of vz plus covariance of epsilon, which is equals to v times covariance of z times v transpose plus v, which is equals to v times v transpose plus v. Figure 6.5. Vectors are independent unit normals that are stretched, rotated, and translated to make up the inputs, where phi is a diagonal matrix with phi on the diagonals. Because the vectors are uncorrelated unit normals, we have covariance of z is equals to the identity matrix with two vectors. For example, covariance of x1, x2 is equals to v11, v21 plus v12, v22. If x1 and x2 have high covariance, then they are related through a factor. If it is the first factor, then v11 and v21 will both be high. If it is the second factor, then v12 and v22 will both be high. In either case, the sum v11 times v21 plus v12 times v22 will be high. If the variance is low, then x1 and x2 depend on different factors, and in the products in the sum, one term will be high and the other will be low, and the sum will be low. We see that the covariance of x1, z1 is equals to covariance of v12, z2, z2, which is equals to, if we take out the v12, the constant, be equals to v12 times the variance of z2, which is equals to v12, because the variance of z2 is equals to 1, and thus the covariance of xz is equals to v, and we see that the loadings represent the correlations of variables with the factors. Given S, the estimator of sigma, we would like to find v and phi such that S equals to v transpose times phi plus v if there are only a few factors. That is, if v has few columns, then we have a simplified structure for S, as v is d times k and phi has d values, thus reducing the number of parameters from d squared to d times k plus d. Since phi is diagonal, covariances are represented by v. Note that PCA does not allow a separate phi, and it tries to account for both the covariances and the variances when all phi are equal, namely phi equals to phi times identity matrix. We get probabilistic PCA, tipping, and bishop 1999, and the conventional PCA is when phi are 0. Let us now see how we can find the factor loadings and the specific variances. Let us first ignore phi. Then, from its spectral decomposition, we know that we have S equals to C times D times C transpose, which is equals to if we separate D equals to the multiplications of two matrices. That will be equals to C times D to the 1/2 times D to the 1/2 times C to the T, which is equals to C times D to the 1/2, then times C times D to the 1/2 to the transpose, where we take only k of the eigenvectors by looking at the proportion of variance explained so that C is the D by k matrix of eigenvectors, and the D to the 1/2 is the k by k diagonal matrices with the square roots of the eigenvalues on its diagonals. Thus, we have V equals to C times D to the 1/2. We can find Vj from equation 6.15 as Vi equals to Si squared minus the summations of Vij squared, summing for all index j starting from 1 to k. Note that when V is multiplied with any orthogonal matrix, namely having the property T times T transpose is equals to the identity matrix, that is another valid solution, and thus the solution is not unique. So S equals to Vt times the transpose of Vt. If we expanded the terms of the transpose, there will be V times T transpose times V transpose, which is equals to V times I, the identity matrix times V transpose. Because identity matrix is T times T transpose is equals to I, then that will be equals to V times V transpose. And if T is an orthogonal matrix, the distance to the origin does not change. If Z is equals to T times X, then Z transpose times Z is equals to, if we expanded the form, Z equals to Tx, there will be Tx to the transpose times Tx, that will be equals to X to the transpose times T to the transpose times T times X, and since T transpose times T is equals to identity. That will be equals to x times x to the transpose times x. So multiplying with an orthogonal matrix has the effect of rotating the axis and allows us to choose the set of x's most interpretable. Ranger 1995. In 2 dimensions, t equals to the set cosine theta minus sine theta, cosine theta. Rotates the axis by theta. There are 2 types of rotation. In orthogonal rotation, the factors are still orthogonal after the rotation, and in oblique rotation, the factors are allowed to become correlated. The factors are rotated to give the maximum loading on as few factors as possible for each variable to make the factors interpretable. However, interpretability is subjective and should not be used to force one's prejudices on the data. There are 2 uses of factor analysis. It can be used for knowledge extraction when we find the loadings and try to express the variables using fewer factors. It can also be used for dimensionality reduction when k is less than d. We already saw how the first one is done. Now let us see how factor analysis can be used for dimensionality reduction. When we are interested in dimensionality reduction, we need to be able to find the factor scores zj from xi. We want to find the loadings as wji such that zj is equals to the summations of wji times xi plus epsilon I, where the summation is summing for index I starting from 1 to d, and the j is starting from 1 to k, and where xi are centered to have mean 0. In vector form, for observation t, this can be written as z to the t is equals to w to the t times x to the t plus epsilon for all t starting from 1 to 3 until n. This is a linear model with d inputs and k outputs. Its transpose can be written as z to the t to the transpose is equals to x to the t to the transpose times w plus epsilon to the t for all t starting from 1 to 3 until n. And given that we have a sample of n observations, we write z equals to x times w plus v, where z is n by k of factors, x is n by d of centered observations, and v is n by k of zero mean noise. This is a multivariate linear regression with multiple outputs, and we know from sector 5.8 that w can be found as w equals to x transpose times x, then to the inverse, then times x transpose, then times z. But we do not know z. It is what we would like to calculate. We multiply and divide both sides by n minus 1 and obtain the following. That is, w equals to n minus 1 times x transpose times x to the inverse, then times x transpose, then times z, then divided by n minus 1. If we combine the term, that becomes the following 2 terms. The first term is the inverse of x transpose times x divided by n minus 1. The second term is x transpose times z divided by n minus 1. So if we do the simplification, by the definition, that will be s to the inverse times v. And placing equation 6.22 in equation 6.21, we write z equals to x times w, which is equals to x times what we have found before, that is x times s to the inverse, then times v. Assuming that s is a non-singular, one can use r instead of s when xi are normalized to have unit variance. For dimensionality reduction, FA offers no advantage over PCA except the interpretability of factors allowing the identification of common causes, a simple explanation, and knowledge extraction. For example, in the context of speech recognition, X corresponds to the acoustic signal, but we know that it is the result of the nonlinear interaction of a small number of articulators, namely jaw, tongue, velen, lips, and mouth, which are positioned appropriately to shape the air as it comes out of the lungs and generate the speech sound. If a speech signal could be transformed to this articulatory space, then recognition would be much easier. Using such generative models is one of the current research directions for speech recognition. In Chapter 16, we will discuss how such models can be represented as a graphical model.